Studio on my PC.
That's better. You pay $20 once for Google Play, you're done.
I actually.
Does anyone still play Go Pokemon Go with a rooted device?
Me? Yeah.
With a rooted device?
You can do it with a rooted device?
Yeah.
Did you update it?
They patched it.
They patched it.
Let's see.
Is your device rooted?
Yes.
But I have apps on my phone, bro.
Well, okay, as far as I'm concerned, I just refuse to play it anymore because if they just say, okay, if you have a rooted device, you have to be a cheater, I'm just going to say, well, I'm not going to play your game. That's
Yeah.
it. I'm not even going to circumvent this and try to avoid my time.
Publish on Google Play. I have a phone. Probably.
So now that wouldn't work because your GPS would change. Your GPS, your license would change.
Yeah.
It would
Okay.
work for-
And my phone is rooted, like, I can smooth my GPS. I can pop up in Japan if I wanted.
You can still do it?
Well, I had to make some major changes to my system. I had to basically change the system apps and install application as a system app, and then I have to create another application if I'm going to smooth this because otherwise I will have a teleport issue where I will appear in one place and then back to my actual location and back. So I have to do a bunch of stuff just to be able to teleport. But yeah, but I haven't played in a while.
Then you download it because I don't have
I stopped it. I'm like, we're tired.
Nope, it is time. So what I'll do today in the lab is I will show you guys how to, design the latches and up to the, well, I can do all three designs. I think we have enough time to do it. Okay, so we'll start with the SR latch first, okay?
Is this going to record audio too or no?
Sorry?
Is this going to record audio or no?
I think it is being recorded right now. Yep, it is.
But the last one didn't record audio.
Yeah, I did.
There
I
was
checked.
audio for last class?
Yeah,
What?
I checked.
What did we miss? What? Never mind. Okay.
Yeah. All right, so what we'll do is we're going to design the SR latch and just play with it, so that we can interactively see what is happening, okay? So in the lecture, I kind of play out the scenarios on the whiteboard by analyzing the circuit and go like, okay, if we turn this into a 1, if the outputs are both 1, 1s, what is going to happen when we specify 0, 0 as the inputs, okay, what is going to happen? They will both turn into 1s and maintain the state. But what if we have 1, 1 as the output and then we turn the input into 1, 1 as well? Then we have a race condition. So that would be kind of a fun scenario to play with in Logisim. Okay, so we'll see how we can kind of emulate that particular situation and see what Logisim has to say about it. Okay. All right. So we'll make a design from the most basic circuit first. So I'm going to pull some NAND 2 gates, making sure the inputs are down to 2 because that's all we need. And we can make it a smaller design so we can make the gate narrower. And then we can zoom in just one more level. There we go. Duplicate the design like so. 2 input pins, 1, and duplicate it one more time over here. And this time I'm going to label these pins as the way we talked about in class, using /S to mean active low set and /R to mean active low reset. So we have this one being /R, and then this one is /S. And then we have the outputs labeled accordingly. One is Q, the other one is /Q. And somebody mentioned that in another textbook it's the opposite.
Yeah. They have, I don't know, they show a lot where the first example they show it's just S and R and Q primes at the bottom.
Okay. Yeah, the prime is negation.
Yeah. Oh yeah, I mean that. It's same thing as complement.
Yep. Okay, so we have all the basic components here. Now we just draw the picture. The picture is pretty easy. Okay, the output of one gate goes into the input of the other one, and then the individual inputs, would also go into either the top or the bottom NAND 2 gate. So we just need to draw these pins the way they are, like so. And then the output pins always go to the output. The output of the gates go to the output pins, but at the same time they also feed into the input of each other. So we have this pin going into here, and then that pin going from here to here. Okay, so now we have a basic SR latch done. Okay, and as you already see, when both inputs are zeros, both outputs become ones. Okay, we talked about this already, and this is really a critical bad state for an SR latch. Okay, an SR latch really should not get into this state because that's not what it is supposed to do. So when we go into simulation mode, we can now switch one into a one. Okay, turn them both into ones, and you can see there are no changes to the state. Turn the other one into a zero, and then turn them both into ones again, and there's no change of the output state. So we have just demonstrated the most basic stuff of an SR latch. What I'm going to do next is to say, okay, what if I turn both inputs into zeros, and then turn them both into ones simultaneously? Because then the output cannot both be ones. One has to turn into a zero. Which one is going to turn into a zero? Or Logicsim would just say, cannot do this. Okay, So we'll see what happens. Okay, but to turn both pins into the same state at exactly the same time, I cannot possibly click on the screen fast enough to do that. So what we'll do is we're going to cheat a little bit here, and just say, no, we just disconnect one of the pins.
And you connect to one pin.
Yeah, just connect to one single pin. So we get rid of this one, and then we say, okay, let's hook up these two together. Okay, so when both inputs are zeros, both outputs are ones. That we know already. So when we change the state of /s in this case, that will answer that question of, okay, what's going to be the output in that case? We know it's going to be a steady state, okay, but it becomes a raised condition. So we go ahead and change it, and it says here oscillation apparent. But there's no actual oscillation because because one of them will turn into a one first. So that should not be an oscillation. Is that okay so far? Sort of? Because we don't like our latches to oscillate. That would not be good. Okay, so we are done with the basic SR latch. Okay, so let me revert the design back to what it used to be. So we'll do a Control-Z, and getting back to here, getting back into simulation, and it doesn't even remember, it doesn't even see that design has changed back into the original design. It doesn't, it just doesn't like it. Yep. Sorry? I don't know how to get rid of the error state.
Go to simulate and reset simulation.
Ah, there we go.
And then re-enable the simulation.
No, that didn't do it.
One of the wires on the top gate is
It's a
disconnected.
bit renewed.
It is?
Yeah, it's disconnected.
Oh, your input?
Oh, this one. How did that get disconnected?
Oscillation broken.
No, well, this can be a Logicsim bug too. So if it, so you just save the design. We just call this latch. Okay. Close.
Either reset simulation and simulation enable.
Oh. Okay.
There you go.
Okay. So we have simulation.
Yeah, it's already set.
Oh, okay, so we have the disable, reset, and re-enable. Okay. All right, so this is a basic latch. So what I'll do next is to turn this into its own little box. Okay, do you guys have any questions back there? You good? All right. So we'll turn this into a design first so that we can use it as a component. So we'll go ahead and go to project and just add a new circuit, and we'll turn this into a circuit first. So we'll add a new circuit. The new one is going to be a D flip-flop. So we'll do a D flip-flop as a new design, and then we'll turn this one into its own circuit. So we say edit circuit appearance, turn this into one little circuit here. And it's probably best to label the pins because otherwise I cannot remember which one is which. So we'll just label this one as /S/R, and then we have Q and /Q. And remember, /Q is usually not used, so the pin is usually, sometimes it's not even brought out to the design. But we'll keep it around because it is a part of the circuit. There we go. Okay. So now we have the main design, and let's change the name of the main design as well. Okay.
If you double click on it.
Change it over here. So we call this a SR latch. There we go. So now we go to a D flip-flop and say, okay, how do we utilize an SR latch as a part of a D flip-flop? So we put one of these components here, and once again we need some output pins. So one output pin going here, and this is really the only one that I need, so I'm not going to specify the other ones. And we also need two NAND 2 gates on top of the ones that are inside the SR latch. So we go to gates, go to NAND, and then we change the number of inputs back to 2, just like before, and then the design back to a narrow one, duplicate, so now we have 2. And then this one, we need the second one to be negated, so we turn that into a negated pin. And then we have 2 input pins to this design. The second one is clock. I'm following basically the same terminology and positioning of the nodes here. And the top one is the data pin. So now the data pin goes straight into this one, but it goes into the negated version in the second one. And then the clock pin goes into both of the pins not negated. So it goes into this one just fine, and then go into the other one just like that. And then we have this pin connecting to the S bar or /S, and this pin going into /R, like so. Okay. And it's complaining there's an error.
You have to change one. There you go.
Okay, so it does work. Okay, good. Just double checking. So when we go back to the D flip-flop, okay, there we go. Okay, so the design is now, operational. When the clock line is a 0, it will just ignore the data pin. I can turn the data pin upside, in any way, and it's not changing the state of the SR latch. On the other hand, once I turn on the clock, then whatever I specified as the data pin is going to change the output right away. Because remember, this is level sensitive at this point. So when I change the data pin, it changes the output, and when I change it back, it will change back the output. Now this is okay, it is useful, but it's not as useful as I would like it, because I want things to be level sensitive and not, I want it to be edge sensitive and not level sensitive. The way it is right now is called level sensitive. Okay? So this is all good, but it's not quite what I want. So getting into the nodes, in Moodle, this is the one that is going to be level sensitive. Okay? So we'll go ahead and replicate this design in the in Logic. Are there any questions at this point about all of this? Yep.
Wasn't the flip-flop the one that was level sensitive and the D flip-flop the one that was not level sensitive?
They're both D flip-flops. The first one is a level sensitive D flip-flop. This one is an edge sensitive.
So they're both
D
just called D flip-flops.
They're all flip-flops.
Okay, there's no special name to distinguish them easily? Like ED flip-flops versus...
This one is just called an edge sensitive D flip-flop, but it's
that long name then.
longer, yeah. Okay, so we'll go ahead and replicate this design. We have 2. Okay, does this look like a SR latch to you?
Mine's like got an error.
Yep, this is a SR latch by itself. This one is not. This is the only one that is kind of tricky. So I'm going to use 2 latches instead of looking into the design like this. I'm just going to use 2 SR latches, and then this one is special, so it's going to be on its own. There we go. All right, so we'll go ahead and add a new circuit, and this one is going to be edge sensitive D flip flop. Okay. Questions?
I like doing it with you, but I have an error on mine. I have to figure out why.
Oh, okay. So we're gonna slap, two of.
Do something here, like save it somehow, because I know the little label that they do.
We'll slap two of these things first, and then the other one is kind of special, so we cannot just do it the same way. So we'll need to pick out a NAND gate, but this time we have 3 inputs, not 5, not 2, but 3 inputs, and then the other one is going to be just 2 inputs. So let me see if I can turn this into a narrow one. Okay, that works. And then the other one only has 2 inputs, like so. And let's see. So they're kind of like a latch by itself. Yep. Mm-hmm.
Can we add just one AND gate to existing circuit?
Say again?
Instead of writing the new circuit, just to add one AND gate to simulate 13.
To simulate
13.
the third pin.
Yes, NAND with 3 pins.
Uh-huh.
So for 13, just to add one AND gate to existing latching circuit.
To the existing latch.
Yes, circuit.
Okay, but the third pin comes from. Okay, so this pin is from here, and then this pin is from here, and then one pin is from the input. Okay, this is the pin that is special because this pin here connects to the output of another latch. So I will have to change the latch design to incorporate that one extra pin. So I decide not to do that, and instead I just draw out the design like this. Is that all right? Okay. So this pin goes to here, and then this pin goes to here. So I'm gonna just draw this out. So we have. So this time we only use the Q bar to go to here, and then we have a single output pin, which is here, and then this one goes straight to /R, like so, and then the input to this is from this one. So it goes here and it goes to the top. It goes to the here. And then this one also has a negated middle one, so we turn this into a negated pin. Oh, I take it back. Nope, that is not the case. Okay. And then with the top one, this one comes from the clock line. So the clock line feeds into the bottom one here. And it goes to the top of this one. And then the middle pin comes from here, from the /R.
This is your main circuit. So you do this over here. This on this, and then you go to that circuit. And then click so.
And then we have a data pin as the input. And it goes straight into this one. And then this one feeds into that one. There we go. I think I got it. Because the top one here is a latch itself. This is a latch itself. This one is not quite a latch because it has an extra pin to one of the NAND gates. But I think this is it. Okay, let's see what happens when I turn the clock to 1. Oh, simulation. There we go. New. Yep, that works. Alright, so the design does work. Instead of following exactly the same circuitry as in the notes, I just combine the top SR latch and use a SR latch in place of that one. And then the same happens to the output latch. So I just turn it into its own SR latch. All right, so what we can do with this is we can now experiment with it, right? Okay, so we turn the clock into 0 first, okay? And remember when the clock is 0, just like with a level sensitive D flip-flop, I should be able to change the data pin however I want to and not affect the output. Okay, do you guys have any questions back there or up here?
I was having a logic sim issue. I couldn't get
Oh, okay.
something sorted.
Well, just kind of focus on the discussion first, because that's kind of the more important part, although it's recorded and watch it later. But you can ask questions. Okay, so when the clock pin is a 0, which means we should not be changing the output, you can see that you can change the data pin. It does affect this pin here, okay, this wire here, but it doesn't actually change the latch itself. Why is it not changing the latch itself? By making the clock 0, okay, the clock being 0 is going to reset this particular latch here. This is the /Q, which is the negated output, which is guaranteed to be a 1. So as long as the clock line is a 0, it guarantees the top SR latch to have a negated output of 1. Okay, so this one is guaranteed to be a 1. What is going to happen to the other two NAND gates where the clock line is a 0? The clock line feeds into the first or the middle NAND 2 gate. Because it's a 0, it guarantees the output to be a 1. So that's why we have 1, 1 going into the SR latch, and that's why when the clock line is a 0, it guarantees that the output SR latch to maintain its state and not to change anything. Is that okay? Yep.
So both of S and R are 1, then it maintains the state?
When both S and R are 1s, it means maintain the current state. So this is where the flip-flop, this is the state that the flip-flop should stay in for the most part of the time, because it's just remembering my current state, but I'm not making any changes. Is that okay? All right. So the question now is, I have a data pin being a 1 here, which means I intend to change the output SR latch to be a 1. So what is going to happen when we have a transition of this clock line going from 0 to 1? Okay. So if I click this to be a 1, we will see a change over here to be a 1, which is not really a whole lot of fun. So we want to reason this out. Okay, why is that going to change to a 1? All right. This is currently a 0, okay? And this 0 is affecting this particular SR latch because it's going into the input of this one, but it's also going into the input of this one. When this turns from 0 to 1, what is going to happen? Well, let's analyze that change, okay? Let's see how that change is going to propagate. When the clock line goes from 0 to 1, the input into the top SR latch, this one will turn into a 1, okay? When this turns into a 1, the other one, if it remains to be a reset, I mean, it remains to be low, it will set the output, which means the negated output is going to be a 0, which means we're going to set the state of the output SR latch to be a 1. Does that make any sense? But what about the other part of the circuitry? How is it going to interact with this design here? When clock goes from 0 to 1, it will also turn this line so that we have 1 over here. But this line is already a 0. And this 0 here is guaranteed because of the data line itself. So it's not going to change the output of this particular NAND 2 gate because we still have at least one input being a 0. Is that okay? Sort of? Okay. So we now know why when we turn this clock line from 0 to 1, it would affect the output. Now here comes the big question. The big question is, this design is, because we could do this already with the previous design, with the level sensitive D flip-flop, we were able to do this already. The special part about this particular design is, if I turn the data line from 1 to 0 at this point, when the clock line is steadily at 1, it should not change the output SR latch at all. The question is, why is it not changing it? Whereas the previous design is level sensitive. The moment we change the D while clock is high, it will change the output. This one should not do that. So let's see what happens when the clock line is a 1 and why it is quote unquote locking the state already, so that we don't have the output latch won't experience any changes anymore. Okay? So let's just say that we turn this D from 1 to a 0. I'm not going to click it. We just want to analyze what's going to happen. When this D line turns into a 0, we will have 1 0 going into this NAND gate here, right? Because this is the only place where the D line is going into, is this, the last or the bottom NAND 2 gate. So this NAND 2 gate will turn the output from 0 to 1 for sure. Okay, that's the one thing that will definitely change. So this goes from 0 to 1, and this 1 is going to feed into this gate here. Do we care?
No.
Nope, because we have at least one other input pin that is permanently a 0. But this one, the change of this 0, this into the 1 into a 0 on the data line, and the output of this bottom NAND 2 gate from 0 to 1 will also go into this particular flip-flop here. So it will turn the /S line of this SR latch into 1 as well. So now we have 1 1 as input to the top SR latch. What is that going to do to the output of an SR latch? Absolutely nothing, because when both inputs of an SR latch are 1s, the output, it maintains the state. Exactly. So the bottom line is, when you have the clock line being a 1, nothing is going to change. You can turn the D from a 1 to a 0. It will change individual gates, but it's not going to change the output here. Is that okay? Yep.
I have a question. What's the point of the first pin on the very bottom NAND gate? I removed that connection and it still gives the same results.
Which one?
The second pin. The input pin, second input pin.
This pin?
Yeah.
So you're taking out the feedback pin from the clock line. I think that has to do with the case when you have you're turning the bit into a 0. It will make a difference in some cases. So the difference is when this line becomes a 0, then it becomes significant.
Oh, I see what it does.
Okay. Is it in the other case when you want to turn from a 0 to when the data line is a 0?
Oh, that's a 0, and then you hit the 1, it'll push it out.
Yep. Okay, so I'm going to click this button here. I'm going to click the data line so it goes from 1 to 0. And you can see that it does change this line here, but the input into the SR latch did not change at all. So this is good because now it is level sensitive. Once the transition from 0 to 1 has already occurred, I can play with the data line all day long, and the output of this entire device does not change at all. Are we okay with this design so far? Okay, so let's talk about what happens when the output is a 1 and I want to turn it back into a 0 in the transition, and what happens after the transition, and then keep playing with the data line, okay? All right, so when I turn the clock line from 1 back to 0, should it affect the design at all? That's the first question, because I want this design to be only rising edge sensitive, but not falling edge sensitive. Rising edge means you're going from 0 to 1. Falling edge means you're going from 1 to 0. Okay, now you can make designs that are bidirectional, which means they're sensitive to both transitions. But in this case, I just want it to be rising edge sensitive. But if I want it to be rising edge sensitive, I have to make sure that it is not falling edge sensitive as well. So now we're just going to kind of go through the mental exercise, and then we'll click it to see what happens. So we go through the mental exercise of what if we change the clock line from 1 to 0 at this point? What is going to happen? Okay, the clock line goes from 1 to 0. So the 0 goes into the top SR latch, and we are going to reset the output, which is asserting the /Q here. Asserting the /Q is not going to do a single thing because the other pin is already in a reset state. Turn it S/S from 0 to 1 is not going to change the output of the SR latch. Okay, so that part is okay. What about the other stuff? The clock line also goes into the middle NAND gate, but that's not going to do anything either. Well, okay, I take it back. Because this line is now a 1, right? And we are turning this from a 0 to a 1, which means the output of this, of the middle NAND 3 gate is going to be a 1 again, because the output of this part is a 1, but the input is turning into a 0. Remember, we were saying that we're
You're switching 1, 1 with another 1.
Exactly, we're swapping the 0 and 1, but we still have at least one input being a 0, which means the output continues to be a 1. So in that case, the inputs into the output SR latch will be 1, 1, which means don't change anything, maintain the current state. So we know the following edge is not going to do anything, okay, which is great. Okay, so we click it and we don't see any changes. So this is good. Now that we are in the state where the clock line is a 0 and the state of the output latch is already a 1, let's see how we can turn it back into a 0, because we kind of have to check all the transitions and make sure they all happen correctly. Okay, so at this point, when I turn the clock line from 0 to 1 again, what is going to happen?
It will turn the output to 0.
Okay, so it affects two components directly, right? So the first component it affects is potentially affects is the top SR latch. But it's not going to do a single thing to the top SR latch, because one input is a 1 already. You're not specifying the other one to be a 1 also. A 1, 1 into a SR latch means do not change the output state. So the top one is not going to change, which basically means we will keep the //s line to be high, which is good, because /s being high means we are not setting the output. Okay, but let's check the middle NAND 3 gate and see what happens when the clock line goes from 0 to 1. Both, it has 3 inputs. Of the 3 inputs, 2 are 1s already. So when the third one, which is coming straight from the input pin clock, is also a 1, then we have 1, 1, 1 as the input of a NAND 3 gate, which will turn the output into a low. Okay, so that means the /r into the output SR latch is going to be a low to assert and say that we want to reset the state of the SR latch, and that will turn the output into a 0. Does that make any sense? Okay. Yep.
So when you say NAND 2 gate, that means a 2-input NAND gate. When you say NAND 3 gate, that means a 3-input NAND gate.
Yes. Yep. Okay, so, but that's not the end of the story, because when we change the state of the NAND 3 gate, the output of that is going to go into the other one as well, so we'll see what happens. Is it going to change anything with the bottom NAND 2 gate? No, because the bottom NAND 2 gate already has 1, 0 coming in from D, from the data input line, which guarantees the output to be a 1, so it's not going to change the state. So that's the prediction, okay? So let's click the clock line to clock high, and you can see the output is now a 0. So now that the clock line is high, I want to play with the data line and make sure that once we have gone through the rising edge transition, the data line can change whatever, can change its state and not affect the actual output. So now we go through the mental exercise first, and then we'll go ahead and actually click it. So now we're talking about the data line going from 0 to 1, and we want to see whether it changes anything significant as far as the output is concerned. Internal to this thing, there might be some changes. So when the data line goes from 0 to 1, is it going to affect any changes?
No.
Absolutely not, because it goes into the bottom NAND 2 gate, but because one of the input of the NAND 2 gate is already a 0, I can change the data line from 0 to 1, and it won't change the output of the NAND 2 gate at all. It will maintain the 0, and it will maintain the output to be a 1. So the rest of the circuit doesn't really change at all when I turn the data pin from 0 to 1. See, there's no changes to the circuit whatsoever. Okay? All right. What about the clock line? The falling edge from 1 down to 0, is it going to do any changes? Let's analyze that. So I'm talking about this clock line here. I go from 1 to 0. I don't want any changes to the output, okay? But we have to kind of make sure that that is the case. Okay. So the first thing you notice is when I turn the clock line from 1 to 0, there are 2 things that are immediately affected by that particular event. The first one is the top SR latch. You guys have a question? Okay. So the first one is the top SR latch. When I turn the clock line from a 1 to a 0, okay, if you follow this line here, it will basically start to reset the SR latch. But guess what? The SR latch is already in a reset state. So that's not going to it's not going to change the /Q output of the top SR latch. So that's good, okay, because we don't want that to change. When we turn the clock line from 1 to 0, it also feeds into the middle NAND 3 gate. This might change something, so we'll see to what extent is it going to change something. The input here will turn from a 1 to a 0, which means the output of the NAND 3 gate will also turn from a 0 to a 1, okay? And that goes into the bottom gate here, from a 0 to a 1. It also goes into the output SR gate, SR latch. So it will turn the output of the input of the output SR latch to 1, 1. Would that do anything to the output SR latch when
No.
the inputs are both 1, 1?
Locks it in place.
It will maintain its state, locks it in place.
You're gonna want it to be 1, 1, so it keeps the state.
Yep, exactly. But what about the bottom one? Because it will also change the output state of the bottom NAND 2 gate. So let's see what's going to happen with this one. So it will turn when we turn the output of the NAND 3 gate into a 1, the bottom NAND 2 gate will have 1, 1 as input, right? Which means its output is going to be a 0. The 0 will affect the middle NAND 2 gate, but that's okay because this one already has one input being a 0 to begin with. Having one more 0 doesn't change its output, so we are safe there. But this signal also goes into the /S signal of the top one. So /S is going to be asserted because it will turn into a 0, okay? So it's going to be setting this circuitry here, which means /Q in return will turn into a low. But this low is going into here. So that means we are setting the circuit. That doesn't make sense. Let me think about it again. So the clock line is going from 1 to 0. So that line is going straight to here. But this state is not changing. Oh, never mind. I misread the picture. I misread the picture because this one turns into a 1. This turns into a 0. Going back here. So it is going to set the top SR latch. When you set the top SR latch, the negated output is going to be a 0. And that 0 is going to go into here. And this one is going to be asserted. This one is going to be high. /R is going to be high to the output latch. So it will change the output.
Oh, well.
Well, /R will also be changed because that /Q feeds back into there, and then you have 3 total, won't you?
Okay, /Q is going to be deasserted, right? So this will turn from 1 to a 0. But this one is going to turn into one of the input is going to be a 0 because the clock is now a 0. So the output of this is going to be a high.
All the 0 inputs.
But this one is going to be a low. That's going to be the problem. Okay, I need to think about this one more time. Okay, make sure the design is still correct. So I turn this one into from a 1 to a 0, which will in return turn this one from a 0 to a 1. So now we have 1, 1 going into this NAND 2 gate, which means the output is going to be a 0. It goes back into here, which means we are setting the top SR latch, which also means the negated output is going to be a 0, and it's going to turn the output into a 1. So this is not correct. Yep.
Your SR on that top one, both be 0. So you get ones at both the top and the bottom of that one. Because your clock pin goes directly into the R, and the clock pin.
Oh, right. Okay. Yeah, you're right. Okay, because it feeds into both of them. So both of the input of the top SR latch are 0s, and as the consequence, both outputs would be 1s. So we'll still have this one here. Okay. Okay. So now the latch will the output SR latch will have 1 1 as input. Okay, good job. So let's try that. Yep. So as a result, now the output latch is safe. It's not going to change anything. But this is also one of the cases where we have both inputs to a SR latch being 0, which I said earlier is not usual. That's not how an SR latch is supposed to work.
When you change the clock pin back to 1, it should change it to 1.
Correct. When we change the clock pin back into a 1, and then the first thing is going to do, well, it would immediately change this one here, so that when this becomes a 1, when the clock becomes a 1, it will deassert the reset. It will do the set here, which means this pin is going to turn into a low, which it would immediately turn this into a 1. Is that?
Mm-hmm.
Yep. So that's how an edge-sensitive SR latch works.
So
Yep.
the reset is what changes it from 0 to 1 or from 1 to 0?
The reset of
The SR latch.
Yeah, when you assert the reset, the negated output will become a 1. But normally you only have either set or reset, but not both at the same time.
Because if you have both at the same time, it's...
Then both outputs will become 1s. Right. Okay. Are there any questions about the edge-sensitive D flip-flop? But why is this useful? I mean, just take a step back. This is the very low level how, right? Okay, when you look at how the gates operate, when we make this change, this is going to be that, and so on and so forth. That's the how. So we take a step back, it becomes a what question. What is this? Other than insanity. What is it?
Memory.
It's an edge-sensitive D flip-flop, right? But in the context of everything else, why do we need this? It's memory, exactly. So we have two types of memory now. One is level sensitive, the other one is edge sensitive. So when you look at this design here, so we'll go ahead and turn this into a design, right? So we'll go ahead and look at this circuit. This is edge sensitive D flip-flop. And we'll go ahead and edit circuit appearance. We'll give it some labels. So we have A is, the top pin is, okay, this is the nice thing about, it shows you in the actual circuit at the lower corner of what it is. So this is our clock line, okay, so we'll label this as clock. And then the other one is data. And then this one is actually the Q, which is the actual state of the cell. Okay. So we label this, and then you go like, okay, now we have one way to remember one bit, okay? Because you can remember a 0, 1, as one single unit. How is this going to be useful in the design when we have to deal with numbers? What are numbers? How are numbers represented in a computer?
Zeros and ones.
Using binary, which are zeros and ones, okay? This can remember the state of one single binary digit, which we call a bit, right? Okay, most people did not know that a bit, BIT, is getting the B from binary and then the IT from digit. So it's a binary digit, okay? Yep. So this is one bit. So how do we turn this from one bit into a multiple bit type of thing?
Should you get the numbers?
Yep, we just gang them up, right? Just chain them up. Okay, so let's go ahead and chain this up into an 8-bit register, okay? We called it register, but it really is a multi-bit flip-flop. So let's go ahead and make that design, okay? So we'll go ahead and say, add another circuit, and I'll call this 8-bit register, okay? So the 8-bit register, you can make it level sensitive, you can make it edge sensitive, it's up to you to decide how you want to do this, but the idea is the same. So in this case, I want it to be edge sensitive. There we go. So we'll just basically do this 1, 2, and this is what you do when you have multiples of 2. You can just kind of copy and paste it like 3 times because 8 is 2 to the power of 3. There we go. So So now we have 8 of these things. The clock line is going to be shared. In other words, they all update at exactly the same time. So one input pin to this whole thing controls the clock, but it controls the clock of every single one of these individual parts. So it goes in here, oops, here, here. But the data pins, I don't want them to go into exactly the same thing. So I want one input pin to go to one individual data pin. And you will probably think, oh, so that means we have to draw 8 input pins. Remember, we can make multi-bit input pins. So that's what we're going to do. So we'll go ahead and I need some more space on the other side. Okay, maybe zoom out and move this a little bit here so I can have some more space on this side. So, so I can make an input pin to have multiple bits. In this case, I wanted to have exactly 8 bits, just like that. But I cannot connect this into each individual data pin because the output of this input pin is 8-bit wide, and yet the input of each edge-sensitive flip-flop is only 1 bit wide. So now we have a mismatch again. So how do we fix this problem? Anyone want to make a suggestion? We have 8. Hmm?
No, you,
Not.
you just make like 8 lines from the one to each one of the
Okay, so we need individual lines here brought out in a certain way, but we have to somehow combine these 8 lines into one single line that goes into the input pins. So what do we do to get this to work? Splitter, very good. Okay, so somebody has been playing around with this a little bit. Okay, very good. So we go to wiring, and they have such a thing called a splitter, which is up here. And this is what a splitter looks like. And right now it's only splitting into 2 bits. So we want it to be a 8-bit input splitting into fan out to be 8 output as well. Okay, so let's take a closer look at what it looks like. This is what it looks like. It turns the one single bus input into 8 individual lines. So now we can just feed these lines into each one of this. So we'll call this one bit 0.
So, I'm sorry.
Sorry?
Shouldn't the fan in, then the bit width in should be 1 or 8?
Should be 8.
Okay.
Because if it's 1, that means you're not fanning out at all. This may not be the prettiest way to wire this up, but it's close. And the last one goes here. All right, same thing for the output. We combine all 8 outputs into one single output pin because that's the interface of your design. So we pick out an output pin, turn it into 8-bit wide, like that. And then we also need a splitter. A splitter is also a merger, okay, because it goes in both directions. So we pick out, okay, the easiest way is to use the one that we already have. So I click on this one, just duplicate it, drag it over here, and then we have to kind of flip it upside down or left side right. So we say we turn it from facing east to facing west, just like that. And hook up the merged end into the output pins, and then bring in the individual wires from the individual D flip-flops as the inputs. Yeah, this part is boring. There we go. I think this is one of the more ingenious designs. I have no idea.
You have to be really, 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 really smart.
I think when you work in the field, you start to kind of understand the material better, so you can start to come up with these things.
But coming up with it like back in the 1900s, that.
Well, but back then, people they don't have Pokemon Go, they don't have a lot of distractions in life as well. And you can keep thinking about this stuff when you're working the field. All right, so we have a design done. So we'll check whether it works or not. The output pins are E because we have to set the states first. So this is a clock line. So we go into simulation mode. Okay, there we go. Okay, so now we can change the state of the input pins.
Something doesn't work.
In yours?
Yeah.
Okay, but I'm just going to test this one first, okay? So I changed the input pins, and you can see the changing the input pins doesn't do a single thing to the output pins until I clock the clock line from low to high, then the output pins change. Then I can clock it back low again, and then I can do whatever I want with the input pins again, and nothing is going to change in the output lines. So the design does work. So now we have an 8-bit register. Okay? This is called a register, which is basically a multi-bit D flip-flop, which is the most basic unit of memory. This is how your computer, inside the processor, can kind of keep track of stuff. Do we have any questions about this type of design? Yep.
So does this deal with 1 byte because it's 8 bits?
Yes, it is 1 byte.
Okay.
Now, a byte, B-Y-T-E, is really a play of the word B-I-T-E.
Yeah.
So a byte is 8 bits. It's just multiple bits.
So then,
Of course, twice a nibble.
Yep.
Twice the nibble.
Yep.
if you've got 8 gigs of memory, you've got thousands.
Yes.
That's pretty.
Well, this is how registers are designed inside the processor. The memory cells are arranged a little bit differently. Okay. So now we have what kind of components in the computer? We have adders, we have subtractors, right? And then we have registers. So out of those things, what kind of fun things can we do just using registers, which basically are memory devices, and adders? What can we possibly do with those things? Which is going to be your next homework assignment.
ALU?
Well, not the entire ALU, but we can do something that is forming the basis of your ALU. Okay. In other words, what we are going to do in your next homework assignment is we're going to hook up these things. When I call these things, I'm talking about a register and an adder. Okay, so we'll hook it up in a certain way so that it can be a counter. Click it, increase by 1, click it, increase by 1, click it, increase by 1. We can do that already because we can feed stuff into an adder. Now, if you want an adder, I'm not going to make you guys make your 8-bit adder out of the equations that we talked about. That might be a little brutal, right?
You can say that.
So in your designs, we're going to cheat a little bit, and we'll just pick out an adder from Logic Sim. Okay. So the adder doesn't really do much. It has 2 inputs, right? The numbers that you're adding. It has 1 single output, which is the actual number, the sum, and it has 1 extra output, which is to carry out. It has 1 extra input, which is to carry in. Much like the adder that you're dealing with. Okay. So we're going to use an adder. We're going to use a register. And then we'll go ahead and wire those things up so that it becomes a counter. And what do you think is going to be, how do we do counting using registers and stuff like that? We need a line that is basically the click, and then what do we do? So I'm going to do the basic design here, which is not really the crux of your homework assignment, so that's okay. So we'll go ahead and do this here. So we'll do a basic counter. So with a basic counter, we have an adder, and then we'll do a basic 8-bit register. And this one is edge sensitive, doesn't have to be edge sensitive, okay? So the question now is, how do we wire this thing up to act as a counter? Okay, what's going to be your clicker? What is going to be connecting to your clicker thing? The clock line. Very good. Okay, so the clock line goes to the clicker, which is, I think, is this one.
The top.
The top one? Okay. So the top one, this is the clicker. It goes into here. Okay. What goes into what connects to the output of this particular register? It's the output of a register. It should go to the input of something.
It should go
The
to
N?
CN, or it
You
should
can use CIN. That works. Okay, CIN works too. Okay. Well, not CIN because CIN is a single pin. It's a single bit. This is an 8-bit output.
So you have to send it to the X or Y inputs to
One of the inputs, right?
clicker.
Okay. All right. So let's go to one of the inputs of the adder. So it's one of the numbers being added.
Okay.
What is the other number that you're adding, and what should we specify as CIN? You're adding 1 each time, so you can specify.
Do a 1 as a constant.
Yep, a constant. You can do the 1 in here, or you can do the 1 in here. It doesn't really matter which one. So we'll go ahead and just stick the 1 into the carry in and put a 0 here. So to do that, you go to wiring, and then you look at constants.
Yeah.
There.
Oh.
So we'll pick one out here. We'll pick one out here. And there are 2 ways to do this. You can specify a 1 as the carry, and then specify a 0 as the actual number. But then it has to be an 8-bit 0. I know it sounds really silly because 0 is 0, but you have to specify this as an 8-bit 0 because it's going into an 8-bit input into the adder. Just like that. Okay, we're almost done. We have 2 output pins that are currently unconnected and 1 input pin that is currently unconnected. So how should we wire up these things?
You should put the data from the output to
The output of the adder.
output of your adder to your edge sensitive chip.
The input of the edge sensitive chip. Like that? Alright. Well, let's see if it works. But I have no idea of what is the actual internal state of the 8-bit register. So I'm going to hook up an output pin just so that I can see what is in the register. Does it make sense? Because otherwise I cannot see the internal state. So I'm going to use an 8-bit pin, output pin, just so that I can tap into the output of the register to see what is its current state. That's all I'm going to do. Is that okay? All right. So now we'll go ahead and clock it. Oops. Yeah, change the hand.
Well, those red wires don't mean nothing.
I think it... Is that the clock pin? It is the clock pin.
Do you need to do an initial 0?
And
Oh, no, you're missing a connection right underneath that.
Hmm?
You have that hanging.
No, he's not missing that.
Yeah. It's
Go back to the
actual little wire
state. Counter.
No, this one doesn't have to go to anything. This is carry out. Yep.
So we need to initialize the register first.
Yes, we do.
So you can change to a constant 1.
I'm adding 1 constantly. That's basically what I am doing.
Inside that.
You don't have a...
That right there.
That register.
That right there should be a 1.
No, that's the clock.
That's the clock, and it has no input right now, so it has to start with an initial state. So that would be helpful. Because otherwise it has no known state to begin with, which is not going to be a good thing.
So if you go back to counter, does it reset it?
And then we go back to counter, and
It doesn't reset it though.
no, let's see, show attributes, view 8-bit register, there we go.
And it just keeps bringing you back to this.
Yeah, because I cannot change that.
So you have to have a way to initialize and then add 1 each time. In counter, not in here.
So this is where
In
a
the counter.
reset pin would come in?
Sorry?
Is this where a reset pin would be used in a real computer?
Yes.
Could you not change the free state so that it's not unknown?
No, well the problem is, with the register, it has no known start state. Each individual bit has no known start state. So when you work a design like that, okay, if I go back 1 level up, it is still going to be a problem because I cannot change the state. And because it feeds back into itself, that means I cannot get the known state from anywhere else because it's an unknown state going into an adder, and then take the output of the adder back into the the same device. So that's why we have a little bit of a problem here. I cannot inject a value to initialize it.
So what you have to do is have a way, you have
To
the
reset.
initial register, you send that data to
Yep.
the ESD flip-flop,
Yep.
and then you have a way to store it back at the end.
Sort of. Yep. So how do we reset, the D flip-flop? What is the quickest and easiest way to reset a D flip-flop? How do I add one more pin to this design? I cannot reuse the pins that I currently have. I need one extra pin, and the sole purpose of that pin is to say, reset to 0, regardless, ignore everything else, just reset to 0. How can I do that?
What part of it are we resetting to 0? The Q?
We're trying to reset that output to 0?
We are trying to reset the output to 0, regardless of what is going on in the rest of the circuitry.
Well,
Yep.
change the output to
No, but I don't want, because the state, because the whole thing depends on D, right? But because we have a feedback in the outer design, you can no longer depend on D to initialize the whole thing. Yep.
You have to short circuit it and put on the final the final what is that, SR latch.
Mm-hmm.
On the not R, the reset, you should have its own reset pointer, its own reset probe or pin.
Okay, so the reset line is normally not asserted, right?
Mm-hmm.
Okay, and how do you, when it's asserted, it is a 1. Let's say when it's asserted, it is a 1, okay? So how can we change the design just a little bit to accommodate one more pin to clear the state to a 1? So let me just put in the components first, and then I'll see whether you guys can come up with the design. So this is clear, and I'm going to use reset to mean clear because otherwise it will look like a clock pin. Okay, so how can we incorporate this pin here, where it is 0? When it's 0, it doesn't do a single thing. When it's a 1, I want it to reset the other circuitry. I want to reset this pin, this whole thing, so that it is a 0. Well, okay, so there are several ways to look at this. We can add one more gate here, okay, so that when this reset pin is a high, we guarantee this one to be a low to change it. When the reset pin is a 0, we make sure that this pin does not change at all, so the other pin will become basically just the input. So that's one way to do it, okay? So let's do it this way. So I'm going to break this connection here because I'm putting in a gate to accommodate for reset. So the reset line, oh, this is going to look ugly. Okay, so the reset line goes out to here. I need some gate to be put here so that the output of the gate is going to feed into here. When the reset line is a high, I want the output to be a low. When the reset line is a low, I don't want the input to be changed at all. It would just take a look at the other one. So what can do this? All right, so we'll draw a picture. So we have the reset, and then we have the other, right? And then we have the output. When the reset is high, I want to not care about the other one, and then the output has to be a low. That's what we want, because this is going to reset the device itself. On the other hand, when the reset pin is 0, and the other pin is high, I want the output to be a high, and when the output pin is low, I want the output to be a low as well. So I will just mirror it. So what can do this? If you just look at these two rows, what does it look like? Blah blah, and the blah blah operator 1 is 1, blah blah. But 0 operator 1 is 1, 0 operator is 0 is 0. What can do that?
X0.
Just a regular OR.
Just regular OR.
Just a straight OR, okay? But what about this one here? If one side is a 1, I want the output to be a 0. The OR doesn't quite do that, does it?
That's the NAND.
Okay, a NAND gate is is, okay, let's look at a NAND gate. What's going to happen with a NAND gate? So when you have a NAND gate, it's not going to work out either. You have to negate one of these two things to make it work. Which one are you going to negate?
The reset.
Okay, so we'll negate the reset here. Okay, so when you reset the reset, when you negate the reset, then the picture goes from 0, 1, 1 here. Okay, so 1 NAND 1 is not 1.
Oh, that's an AND.
Okay, so you just want an AND here, regular AND, right? So a regular AND will work by negating reset. Okay, so this is how you work out what type of circuitry you need. You look at the truth table first. What do I need for each possible case? And then you just work it out like that. Okay, so with an AND gate, a regular AND, not negated AND. So we pick out an AND gate and make sure the input is only 2. Change the design to narrow so it doesn't take up all the space. The reset pin has to be negated first. So I will turn the bottom one to be negated and make sure they're connected. And then the top one is just this guy here going into here. And then the output goes straight back into here. Whew, there we go. But now we have the capability to reset the content of a memory module, okay, which is going to be handy. How is that going to change the overall design?
Wow, additional.
So when you look at the design here and you say, okay, edit circuit appearance, now we have 3 pins because we just added the reset pin. So we'll go ahead and label the reset pin here. And it is it's not negated, it is a non-negative signal, so it's just R. And now the other design would change as well because now everything has 3 pins and they're all connected incorrectly. because when we change the design, it shifts the pins, and so now they're all kind of hooked up incorrectly. So we'll okay, so we'll go ahead and we'll just delete a whole bunch of wires.
Don't you just have to add an additional input pin?
Huh?
Don't you have to just add an
Yeah, we do, but it's also hooking up these data pins to the wrong part. So we need some major, editing here. Yep.
Oh no, with the reset.
Yeah, because they all went to the wrong place because of the offset.
Couldn't you have just swapped them around in the design?
Yeah, I feel like you could have just like.
Yeah, you can just swap the design too.
There is a problem with reset, unless
You missed the.
well, there's another technical problem with reset.
Okay, let's test it first, okay? So let's check whether reset works. Okay, reset. Okay, that's good, right? Okay, so we'll go ahead and put a 1 in, and then see if it resets. Yep, it does. So the reset pin works the way it's supposed to. It's always good to check first. And then we just have to keep drawing this picture. Okay, so those are the data pins, and then we have all the reset pins connecting to the same input pin. So that's an easier one because they all hook up the same way. There we go. And then we need 1 extra pin for reset. So here's my reset pin. Going to here. That's all I need, I think. Yep. So we'll double check the design first, okay? And clock it. The output change. Oops. That's the clock. Uh-oh. That's the clock. Okay, let's see. This one works. So when we go back to the 8-bit register, what am I missing? That's the clock pin. So when the clock goes high, the output should change already. Oh, okay. That's why. These pins became unconnected. Because when you change the design, when you shift the pins around, I think it would actually disconnect the pins first. So even though they appear to be connected, they're actually not connected. The reason why I know they're not connected is because when I move the design, they don't go with it.
You said all you have to do is just drag off and drag back.
Not quite that
No,
easy.
like,
You have to do it like this. You have to reconnect
click
them.
on like the wire, like, and then just drag it away. Drag it away, and like that way.
Yeah. The other way too. I know what you mean, but now they're connected. What? You mean this way?
Yeah,
And
and
back?
back to it.
Nope. Ah, okay.
So,
Yep.
is this how like cin.clear works when programming in C++?
Clear the registers.
Or clear the flags? It probably doesn't use. Never
You're
mind.
talking about in C++, you know, I mean, with that stuff.
Okay.
Never,
So
never
far
mind.
up.
That's never mind.
In C++, when you use cin,
You see and clear. You
Yeah.
clear what's in the buffer. Does that?
It's a member.
it clears the error flags in cin. But when you first run the program, cin as an object, it has already gone through its own initialization. So the initialization, when you first create cin, which is a global object, that will do the initialization already. All right, so clear. Okay. Clear the output. No, it's still not connected. I think some of these wires are not connected. Ah. So that did not work.
Oh my God, he does not like you.
I can't get it to work on mine.
It just won't attach. It is kind of weird. Well, it's not attached. That's the problem. Okay.
Maybe if you just save it and close and open your lines.
Yeah,
Remember
sometimes you have to do
I had
that.
that problem before, and you just save and close and open, and then it's not arguing.
Okay, so do you think it works now? Let's see. Nope. How about that? Nuke it, exactly. Just move everything over, make space, and then pop it back in. Okay, check one first before I do the same thing to everything. No, it's not working. All right. I guess this would be something that we can.
He's got the square on the right side.
Doesn't really connect for him.
I know the design itself works,
The
right?
design's right. It's logic wrong. It's not making connections. It's not making connections.
Yeah, I think we just nuke the design and start from scratch. We'll do that on Thursday, so I'm not going to waste your time today. But the basic idea is that, okay? And then the basic idea of making a counter is really just hooking up a register with an adder, and then you just clock it. So every time you clock, it will update the output, and because it's edge sensitive, that means you won't be changing constantly. Because if it's not edge sensitive, if it's level sensitive, then the moment you turn the clock high, it will keep updating itself because the register is basically a straight pipe going from the input to the output and is connecting to an adder. So the adder will do its work, feed back into the register feeds back into the adder, and it just keeps going. So you need something that's edge sensitive to make that work. And that's also one reason why edge sensitive is useful. Okay. So I'll work on this when I'm home. I'll finish this design here. I'm pretty sure most of you can get this done the same way as well. So I'll meet with you guys on Thursday, and then on Thursday we'll have the new homework assignment based on this.
So for Thursday, should we just catch up on the reading and check out the new
Yeah,
material?
catch up on the reading, especially understanding the latches, the SR latch and stuff like that, because we went through a lot of the kind of details today, so it might take you a little bit more time just to absorb it. So on Thursday, we'll start with the knowledge of latches and flip-flops, but then we'll start to connect components on Thursday. Alrighty, I'll see you guys on Thursday. Have a good lunch.